Hi math students, it's Miss Carol and we are just finishing up Unit 5. We are on Lesson 25. We're still dealing with that nasty flu epidemic and we have 4 questions remaining. So the first question, we're going to go again back to that original function that we had where f of x is 2 times 5 to the x plus 6, and this is the graph of that, okay? The function g of x equals 30 times x, and that's shown in this graph below. It has been defined to model the number of vaccines that can be produced and administered by the community health department. So we want to determine the rate of change for each function over the interval 0 is less than or equal to x, which is less than or equal to 1. So basically, let me get my pen going here. Basically, I want to know the rate of change of this linear function from here to here, okay? And I want to know the rate of change for this exponential function from here to here, okay? So let's do that exponential function first. So I want to know, or I already know, I guess, that when I know that f at 0 equals 8, right? So I know that when x is, I'll just do a little table here, x and y, when x is 0, y is 8. So how about f at 1? Because that's the next thing that I want to know. I can see in my graph it's a little less than 20, but I want to know what it is for sure. So f at 1 equals 2 times 5 to the first power plus 6. 5 to the first power is 5, so 2 times 5 plus 6. 2 times 5 is 10, plus 6, 16. So when x is 1, y is 16. And if you'll remember, the rate of change or slope formula is the change in y over the change in x. So change in y is 16 minus 8. Change in x is 1 minus 0. So this becomes 16 minus 8 is 8 over 1, which is just 8. So the rate of change for the exponential function is 8, and the rate of change for the linear function is going to be the same no matter what interval we choose. And remember, this is a y equals mx plus b situation. So m is our slope or our rate of change. So y equals 30x, and we're crossing the y-axis here at 0, so b is 0. We don't write it at all. So m is, oops, kind of cut that off, but m is always going to be 30 for this particular linear function. And we could prove that because we can see that we're right here at 30. So 30 minus 0 over 1 minus 0 is simply 30. Okay, so the way I would enter this in is I would type 8 first because that's the exponential function, and then 30. Okay? Going down to question 2. So these are a table of values. So x and f of x, where f of x is essentially y, and x and g of x, where again g of x is essentially our y value. So now we're going to do pretty much the same thing, but we are going to find the average rate of change over the interval 0 to 3 instead of 0 to 1. So again, our g of x is going to be 3. So our slope or our rate of change for this, m equals, not 3, sorry, it's 30. And we got that because we had y equals 30x, or g of x equals 30x. So that slope is always going to be 30, just like it was for question 1. Now question 2, this exponential function does not have a constant slope, so we're going to figure out what it is. I'm going to say from our range, from our x range or our domain values of 0 to 3, okay, our y values go from 8 to 256. So this is 256 minus 8, okay, because this is y2, y1, x2, x1, if you remember our formula for slope. So we plug that in, 256 minus 8 over 3 minus 0 becomes 248 over 3. And if I put that in my calculator, I get 82.7. Okay, you could round that to 83, but I think the more appropriate answer here is 82.7. So those are our two rates of change over the interval 0 to 3. So I'm going to go ahead and type that in there. The first one was 82.7, oops, 0.7, and the second one, again, was still 30. All right. Okay, let's erase these and move to question 3. Review your answers to the previous two questions and identify which function has a faster rate of change over each interval. Then explain which function will have a faster rate of change as the upper bound of the interval increases as we go to 5 or to 10 on time, okay, which is our x. So for the first one, our slope was, our slope on our linear function was greater. So g of x had a much faster rate of change than f of x. But then as we got into day 3, our virus kind of took over and our exponential function took off, and f of x had a much faster rate of change than g of x. So what I would say here is that g of x has a faster rate of change in the first interval, which was 0, and I can't do a less than or equal to, so between 0 and 1, but f of x has a faster rate of change for the second interval, which was x is greater than 1, essentially. And so as x increases, f of x is going to continue to have a much higher rate of change. Okay. And again, this should be pretty obvious from the graph. This is going up at a constant 30, and this thing just starts skyrocketing. Okay. All right, last question for our Unit 5 project. Develop a solution for stopping this epidemic. Use your knowledge of how quickly the flu spreads compared to how quickly the vaccines can be administered. So what I would say in this situation is let's get on those vaccines as soon as we possibly can. So let's administer more vaccines during the time when g of x has a faster rate of change than f of x. So that's that initial time period. We could also request that infected individuals stay home to hopefully shift the exponential function. Okay, So I think either of these answers would be sufficient. I think that in terms of this particular question, how you compare the f of x and g of x, the better answer here is probably to administer more vaccines during the time when g of x has a faster rate of change than f of x. Okay, that is it for Unit 5. Once you finish this problem, you can submit that and I will get it graded. I will look forward to grading your projects and I will see you back here for Unit 6. Thanks for joining me.